Morning, everyone. I'm Dhanush. I'm a second-year PhD student working with Professor Karen Scrivener at EPFL, Switzerland. So today I'm going to talk about evaluating the applicability of R3-Reactivity when it is applied directly on the blender systems. Okay, before I talk about reactivity and blender systems, let me first try to convince you all what we are doing is important, or at least convince myself that what I'm doing is important. So there is a lot of buzz around clinker substitution. I would like to think of it in two ways. There is a push from the industrial side where lots of industries are investing in the alternative materials, and there are lots of startups in our space too that are coming every day. It is a good thing, and another good thing that is happening is the regulatory push to clinker substitution. If you look at recent bill from the US government, they declared a $1.6 billion investment in the cement and concrete decarbonization, which is huge. And I would also like to point out that 3 of those 6 projects are concerned with LC3, limestone, calcined, clay cement, which is also dealing with clinker substitution. So I would like to make it clear that it's not just us in the lab who are working on clinker substitution, but everyone outside is also looking to make it clear. And for a second, sorry to make you feel dizzy, but here I would also like to bring attention about the standards, what European standards have been doing and are planning to do with the clinker substitution. On your left, this standard over here has been standing for almost 25 years with almost 27 common cement types. And on your right, there are 2 standards. One allows for the usage of limestone, calcined, clay cement, and the other is the recycled concrete fines. I'm going to talk about these materials, so I put them here. But what the main message is that there are a lot of common cement types, and there are many more upcoming cements. So what it implies for us is that the cement composition is being diversified, and there is also an increase in the clinker replacement for a given blend. So this calls for a good performance evaluation of binder, and this can be categorized in 3 main areas with respect to reactivity of the SCMs, the mechanical performance, and durability performance. So my talk over here is concerned on exploring this link between reactivity of SCMs and the mechanical performance of the blends. But my main PhD topic is durability. If anyone wants to talk about it after the talk, I'm happy to share some ideas. All right, so let's get into the reactivity testing. There are a variety of reactivity testing in the past, but recently many of them reached consensus about R3-Reactivity test being one of the efficient methods to understand the intrinsic reactivity of an individual SCM. So what we do in short, what we do in R3-Reactivity test is we have an SCM, we let it hydrate in the presence of excess calcium hydroxide, as you can see here. These are the mixed proportions, by the way. In excess calcium hydroxide, also in the presence of carbonates, alkalis, and sulfates, system similar to cementitious system. And we will measure either the bound water or the heat signal at heat signal run for 7 days at 40 degrees Celsius. So these graphs over here are the benchmarking tests of R3-Reactivity test, and huge amount of work has been done by RILEM organization, and they made sure that this test is replicated with many kinds of SCMs. As you can see on the right, there are the graph on the right is like an envelope of R3 heat for different kinds of SCMs. And on the left, the R3 heat is measured for individual SCMs also, in the sense that the R3 heat is correlated with the compressive strength with 30% replacement of the respective SCM. So with this background, I would like to introduce you to the problem statement is that so far we've been measuring the R3-Reactivity heat of individual SCMs, but say we have ternary blends or quaternary blends where more than one SCM will be used. So in that case, can we test the intrinsic reactivity of those combined blends instead of individual SCM? So this is the problem that we are trying to solve. I would like to get to the results, and first with materials. Of course, I've been using LC3, limestone, calcined, clay cement. For those of you who don't know, LC3 cement has been first formulated and developed at a lab at EPFL. And here is a picture of a cement bag with LC350. 50 refers to the amount of clinker replacement. So 50% of clinker is replaced with calcined clays and limestone. Here it is 2:1 replacement. As you can see, is 30% is to 15% of limestone. So it is 2:1 replacement. Apart from LC3 mixes, in this study, I also worked on recycled concrete fines. I got these fines from a company in Netherlands. And in Europe, almost 350 million tons per year of construction demolition waste is being produced. And we need to tap into this, and we need to tap in the potential of this demolition waste and try to turn them into something useful. So the recycled concrete fines that I was using had heat, R3 heat, individual heat of almost 100 joule per gram SCM. And to visualize how this performs compared to, say, other SCMs, I would like to bring back this heat envelope graph. And if you place the R3 heat of the recycled concrete fines, as you see on the right, it is performing equivalent to a lower end of natural pozzolans. So it is not completely unreactive, but it's not very reactive. It's in the between. So what we decided is that I'd probably use this as a replacement of limestone in the LC3 system. And if I'm replacing the entire limestone in LC3, I should probably call it RC3, right? So RC3 here, R refers to the recycled concrete fines. And the proportions of the mixes are LC350, RC350 with two different calcined clay to filler ratios. As you can see here, one is the 2:1 blends and the other is the 1:1 blends. And in the R3-Reactivity test as well, as I mentioned, instead of the individual SCM, we put the entire blend in itself, both the calcined clays and fillers in their respective ratios, and we do the same for the compressive strength and look at the correlations in the results part. Another variable that we try to vary is the clay kaolinite content. As you can see, 3 clays were used, C1, C2, C3, with different percentages of equivalent kaolinite content. Clay 1 has the highest kaolinite content, and it refers to higher reactivity compared to clay 2 and clay 3. And the fillers are limestone and 2 recycled concrete fines. So we have 3 clays, 3 fillers, 2 blend ratios. In total, 18 mixes were tested for R3-Reactivity test and mortar compressive strength. So let's look into the interesting part, that is the results. So here I'm going to show the 28-day compressive strength versus the 7-day heat. Here it is joule per gram SCM, but I would like to make it clear that it is joule per gram blend instead of SCM because I'm putting in the combination of blend. And these are the results for the 28-day strength. And the trend lines are separated for both 2:1 blends and 1:1 blends. And you can clearly see that the correlation is good for the 2:1 blends between 7-day heat and 28-day strength, while the correlation for 1:1 blends is bad. And the same story is repeated when you correlate 7-day heat and 90-day compressive strength, where R-square values decreased a bit, but more or less it is the same that 2:1 blends are almost very well correlated. Let's look into a closer look of 28-day compressive strength versus 7-day heat, and this is the trend line that I showed. Is there something evident from this? I think it is clear that we have clustering of data where 3 data points are on the top and the rest are in the bottom. So I would like to make it clear that the top data points in the green are actually corresponding to the blends corresponding to highest clay kaolinite content. So it implies that kaolinite content of clay dictates both the 7-day heat and compressive strength development for at least 2:1 blends. And all the other blends are with the clay contents with 50% and 40% kaolinite content. So what this means is that, say you have like X number of calcined clays and Y number of fillers, and you want to narrow down your options, or you want to narrow down your combinations, you can just do 7-day R3 heat and look at the heat signal and decide if this blend is good enough to give you a good 28-day compressive strength or not. So I think this is really useful in narrowing down your blended options. So I would also like to think of it like a primary screening of blended systems when you have 2:1 blends. But things get more interesting when you go into the 1:1 blends because I don't know what to think of this data, but all I can say is that for the similar heat on the x-axis, you see a shift of almost a variability of 10 megapascals in the y-axis. So it means that there is a variation of 10 megapascal of strength for similar heat values. And this case is different from the previous case because here we are looking at 1:1 blends. And if you remember, 1:1 blends are the blends with higher filler content compared to the calcined clay, compared to 2:1 blends. So this could be explained. I think this variability could be explained by microstructural characterization, which is a plan to do in the future. But I have a small hypothesis inspired from the literature too that Aluminate phases are responsible for rapid heat evolution, and so in the R3 heat, it could be that more aluminate phases formation can lead to higher heat signal, but the contribution to the strength might be lesser. So this needs to be validated with the microstructural characterization. Another thing to note is that recycled concrete fines have variable properties. When you do strength tests with the same sample twice, the results might not be as similar as we think with other SCMs. So there are some kinds of challenges to deal with, but this will be dealt with in my future, where I'm going to do the study of the evolution of phase assemblages using XRD, and also look at microstructural aspects, look at porosity aspects, and also extend this study into other traditional SCMs, because so far I've talked about LC3 and RC3, but we can also extend this and see how the combination of blends of other SCMs are performing with respect to R3 heat. So in conclusion, I used calcined clay and filler in different ratios. When I used it for 2:1, I realized that R3 heat can be directly performed on the 2:1 calcined clay to filler blends, and it can be used to estimate the strength potential, or it can be used to do the primary screening of the blends. On the other side, 1:1, I would really not suggest to do that, and there are unreliable strength estimations, and this needs to be explored more via microstructural characterization. What about in between? What about 1.5:1? What about the ratios in between? I absolutely have no idea, but this is the research in progress, and this is what we are trying to do and extend this to other SCMs. I'd like to acknowledge Professor Karen Scrivener and my postdoc mentor, Dr. Beatrice. And this project is part of Marie Curie, European Union's Marie Curie doctoral networks called Detox. And I would like to thank all the partners, and thank you for listening to my presentation. I'm open to questions. Thank you.